Okay, so in section 1.3, we're going to be looking at the complex field and Euclidean spaces. If you've taken a linear algebra course or an abstract algebra course, you've definitely seen those two topics. And we're not going to go much into detail in these, but we do need to mention some properties and definitions that we might use later on in this class. So, with a definition. And a definition of a complex number. It's just an ordered pair of real numbers, A, B, where they're both, real numbers. A and B are both real numbers. Here, I do need to make a distinction. AB, sorry, I shouldn't have a comma there. AB is not equal to BA, right? Because these are ordered pairs. Order matters. Obviously, unless if B is equal to A, then in this case, these two are equal. So just have that in mind. That is what a complex number is. And something about them is if we let x be the complex number AB and y be CD, we write that they're equal if and only if A is equal to C and B is equal to D. Okay, so that's how two complex numbers are equal to each other. Another thing is we're going to define addition for complex numbers, like as it shows here, and multiplication as it shows here. Okay. Next is a theorem. And these definitions of addition and multiplication turn a set of all complex numbers into a field, right? Where 0, 0, this ordered pair here, this complex number, is in the role of 0, and 1, 0 is in the role of 1, if you want to relate it to the real numbers. So here, to prove this, we would need to just, verify all the field axioms, right? So in this case, I won't prove it because it's just long and it's just little proofs that you can do on your own. It'd be I guess a good but tedious exercise. But we have another one. It says for any reals A and B, we have that these two complex numbers A0 and plus B0 is equal to A plus B0, and their product is equal to AB0. Right, and I mean, again, that proof is trivial, just use the definition. So we're going to go on to define I. So I is a complex number 0, 1, or that ordered pair, 0, 1. That's how we're defining I. Here comes a little, I guess, easy theorem you can prove on your own as well by just using the definition of multiplication. That I squared is equal to negative 1. You probably remember that from high school math, where they just told you that I squared is equal to negative 1. Well, here we define a multiplication. You can easily verify it. This one's a bit juicier, so to speak. If A and B are real, then the ordered pair is equal to A plus BI. And again, this maybe you learned this in high school, but this is an actual theorem. We just don't say AB is just A plus BI. Okay, now we move on to the definition of conjugate. Again, more high school math. If A and B are real, and Z is a complex number A plus BI, then the complex number, Z with a bar, Z bar, is equal to A minus BI, meaning the conjugate of Z, is called the conjugate of Z, the Z bar. The numbers A and B are the real part of the imaginary part of Z, respectively. So A is the real part, BI are the imaginary part, or B is the imaginary part. So we occasionally write A equal to RE, which is real part of Z, and B is equal to imaginary part of z, or im and then z. That's all a conjugate is. We're just switching this plus sign to a minus sign. Okay. Now we have a theorem. This one, these are a bit more fun to verify. But A, B, and C are, well, pretty much just trivial. You can try them on your own. And to prove D, write Z as we did in the definition up here. And then just note that Z times its conjugate, wow, that's separated. That Z times is just A squared plus B squared. That should help you prove D. But we will be moving on to another definition, which is the definition of absolute value. So if Z is a complex number, its absolute value, and that's written as the same as a real number, is a non-negative square root of Z times its conjugate, which we can write as Z times its conjugate to the 1/2. Right, and we just take the positive square root, or the non-negative square root, actually. That's just how we define the absolute value. Okay, now we have a theorem, and here I will include a proof, just because I haven't been including any. But our theorem states, let Z and W be complex numbers. Then we have the following property. So for example, A says the absolute value of Z is greater than 0, unless Z is 0, unless our complex number is 0, in which case the absolute value of 0 is just 0. Another thing is the absolute value of the conjugate of Z is equal to the absolute value of just Z. C is a bit more interesting. Well, actually, we've probably learned this in the class before with real numbers. Absolute value of Z times W is the same thing as the absolute value of Z times the absolute value of W. And then we'll the following D and E that are a bit lengthy to read, so I'm just going to let you see. But we can prove one. Just to make, I mean, we should prove all of them, I should say. But A, B are, well, quite trivial. So we're going to go with the proof of E. And I didn't write it down here, but we're proving E here. This one's a bit more interesting. And to prove E, we're going to note first that the conjugate of Z times W is a conjugate of Z times conjugate of W. So if we add those together, we get 2 times the real part of Z times the conjugate of W. Okay, so we have that Z plus W squared, right? So over here on E, on the theorem, we have Z plus W. In this case, we have it squared is equal to Z plus W times conjugate of Z plus conjugate of W, which, I mean, it's a not a lengthy process, but just a process, just some simple algebra to get this equality, this next expression. And what does that equal to? Well, that equals to the absolute value of W, of Z squared plus 2 times the real part of Z times W squared. I mean, W, the conjugate of W, plus absolute value of W squared. Okay. And that is less than or equal to, then if we were just to take, let me erase here so I can show you. If we were just to take this part, well, this is less than 2 times the absolute value of Z times the conjugate of W, which is why we have less than this next expression. And what is this equal to? Well, this is just equal to so this next expression. And the reason being is, well, absolute value of z squared, that stays the same. So does the absolute value of w squared. So these stay the same. But these down here, well, we're just using the property of c and of b to get to this next equality. So we're using both c and b. But now this is useful because now we can write that as absolute value of z plus absolute value of w squared. Right? And what can we do now that we have this expression and this expression? We just take the square root, right? To take out that squared. And now showing e. Okay, so now we're going to be moving on to something a bit more interesting. We're going to prove a quite big theorem, I should say. But first, we should note that if x1 all the way to xn are complex numbers, we just write their sum as it shows here. That's if we were to add all the complex numbers. Okay, so this is a theorem called the Schwarz inequality. So any theorem that even mentions a name means it's pretty big, and maybe it's used a lot, probably used a lot. So here, if a1 all the way to an and b1 all the way to bn are complex numbers, then the sum absolute value of the sum of all a's and the conjugate of all b's. So, sorry, let me say that again. Okay, so if we were to multiply every aj and the jth component corresponding to the bj, corresponding jth component, but the conjugate of b, if we were to multiply those and then add them all up, then take the absolute value and then square it. I know that's lengthy. It's probably just easier to see it and understand it yourself. Well, that is less than the sum of absolute value of all aj squared times the sum of all bj's, the absolute value of all bj squared. So if you want, go ahead and pause it so you can kind of understand what this inequality is saying. But it shouldn't really be too hard to understand. We're just dealing with complex numbers, adding them up, maybe multiplying. No, we're not using operations that you don't already know. Okay, but we're going to prove this step by step. As you can see, it's not a short proof, but it's not a long one either. We're going to start out by letting A be this here, and by letting B be this stuff over here, and C is what's inside here. And as it mentions here, J runs over the values 1 through n, since we didn't include the J equals 1 all the way to n. It's just something we should already know. Okay. So if B is 0, well then that means that all the B sub j's were 0, since we're taking the absolute value. So the conclusion, well, it's trivial, right? 0 is less than or equal to 0. So we're going to assume, therefore, that B is greater than 0. And, well, from a theorem from the last, we have that this sum, absolute value squared, we could just rewrite that like this. And here, well, we know this is positive. Here, call this z, z conjugate. By a previous theorem on the last slide, the product of z times its conjugate is always positive, right? Except for when z is equal to 0, but in this case we're assuming b is greater than 0. So these should be greater than 0 and therefore positive as well. Right, but from here we go to our next equality. And this one's just pretty much, using algebra to be tedious to verify. But you can do it just as we do multiplication with the real numbers. With complex numbers as we defined it. And we'll just using properties from the theorems we saw from the last slide. So go ahead and pause. It'd be a good exercise to kind of verify these. I do remember verifying these on paper. It took me quite a while. But this is a proof that's worth the time, I should say. Because once we clean up, it looks like b squared times a minus b times absolute value of c squared. And here, well, I could just take out a b, right? Factor out a b. So we have b times ab minus absolute value of c squared. And what do we notice that what do we notice about each term in the first sum? Well, we notice that each term in the first sum is non-negative. Right, so, I wrote it here. We see that b times ab minus absolute value of c squared is greater than or equal to 0. Right, so absolute value, obviously always non-negative. And so looking back down here, b times ab minus absolute value of c squared is greater than or equal to 0. What does that tell, or what do we know about b already? Well, that b is non-negative, right? Sorry, not even that it's not negative. That b is greater than 0. So if b is greater than 0, what does that mean about this? That means that this is either greater than or equal to 0, right? And this is our desired inequality. Why is it our desired inequality? Well, because we can just do algebra, right? And it shows now that AB is greater than or equal to C squared. And that's exactly our theorem. That's exactly the Schwarz inequality. Therefore, proving this theorem. And if this proof is a bit confusing, it's maybe mostly because, that tedious grunt work should be done. And it's honestly good practice to get used to these complex numbers and kind of see how they, I guess not behave, but what properties they have and how multiplication and addition works. Okay, so now we're going to be moving on to Euclidean spaces. So we're going to define what a coordinate is. So for each positive integer k, let Rk be the set of all ordered k tuples such that, well, like x, that it's boldface. So a lot of times we call that a vector, such that it has x1, x2, sort of like a list, right? All the way to hk, where x1, x2, all the way to xk are real numbers. And those are called coordinates of x. And again, usually we call that x, boldface, x vector or a point. Here, if y is that vector, y1 all the way to yk, that list. And if a is a real number, well, then we add vectors in the following way. And here it's a real number times a vector x. Actually, that x should be boldface, my mistake. I'm going to put it x there. Alpha times the vector x is kind of just like distributing the alpha to every coordinate. That's how we do multiplication, the scalar multiplication. And both of these should be closed in RK. Right, so x plus y, that sum should be in RK, and the scalar multiplication of the real number alpha times our vector x should also be in RK. That's how we define addition and multiplication in Euclidean spaces. Next is an inner product. Sometimes we call it the scalar product of vectors x and y. And all we do is, multiply the corresponding coordinates and then add them all up. That is our inner product. Also, we have the norm. A lot of, intuitively, a lot of teachers or professors say the norm is the length of a vector. But we define the norm by putting like the absolute value of that vector. And the way we do it is just square it and then take the square root. If we had, our list x has, x1, x2, so on and so forth, all the way to xn. In this case, you would square each component and then add them up and then take the square root. That's what this is saying down here. So that's the norm. Again, you've probably already seen this. That's the norm in a Euclidean space, the usual norm. You've probably already seen this if you've taken linear algebra. And now we have, well, some theorems that come along with it. So suppose x, y, z are vectors in RK and alpha is a real number. Well then, x, the absolute value of x is greater than or equal to 0. That's not the absolute value, is it? It's the norm, right? So the norm of x is greater than or equal to 0, as we saw down here. That's how we, denote it. The norm is 0. The norm of x, is 0 if and only if that vector is a 0 vector. Other properties we saw similar that we saw last time. Same thing over here. We have something that you might know as a triangle inequality. And the same here. Okay, so we're going to prove E, right? Seems like I like the letter E, so we're going to prove E. So by D, these should be proven in order. So we should already know that A, B, C, and D are true. And you can verify that on your own. Try to prove them. Again, there shouldn't be more than a couple lines. Well, by D, we have that x plus y squared is equal to x plus y times x plus y. Right, we're just using this D property here. And we have that, well, here, sorry, I should backtrack a bit. Here, this is non-negative, also non-negative, non-negative, no need for the absolute value. So let me backtrack and not say D yet, right? So this is going to apply to the whole theorem, not just to this line. That may be a bit confusing. So that's why I'm backtracking. But anyway, so now we have that this is equal to x times x, just as we're doing multiplication, plus 2xy plus y times y. Right? And now we can use D. Because here this is less than what? Well, x times x is just x squared. But now here we can use that x times y, d, is less than the norm of x times the norm of y times 2. Plus, and then y squared, that's the same. And what is that equal to? Well, that's just equal to x plus y, the norm of x plus y, squared. And from there, well, we can just get rid of this squared by taking the square root, which shows that x plus y, the norm of x plus y, is less than or equal to the norm of x plus the norm of y, which shows e.